Well, hello guys. It's time for us to look at some sketching and transformations of sine and cos graphs. So I hope you get something out of this. It's a big presentation, so buckle your seat belts and let's go. I'm going to show you in this first little bit of the presentation how you actually generate the graph of sine, and I'm going to sort of create a little animation for you doing that. Now what I've got here is a unit circle, and I've got our little triangle here. This is the hinge here, this is the movable point. We're going to move around here and generate further and further positive angles with the positive direction of the x-axis. And what I'm going to do then is I'm going to show you how to turn that into a graph, because this brown graph traces out the sine theta as the angles, because this horizontal axis shows the angle that we're making with the positive direction of the x-axis. And similarly over here, this is the negative angle we will be then making subsequent to the first part of it with the positive direction of the x-axis. I'll show you what I mean if this doesn't make sense. Here we go, look. Oh, by the way, I'm showing up here the angle we are making with the positive direction of the x-axis, alright? Now, okay, I've created an angle there, this is the angle there, and basically we're going to trace out the value of sine with moving horizontally along this axis to represent the angle that we are making with the positive direction of the x-axis as we do that. And the value of the y value of sine will be the equivalent of this vertical red line here, because remember this is a unit circle. Red line over hypotenuse, and the hypotenuse is 1. Okay, so you'll see this little gremlin here moving and tracing along the curve as we generate more and more positive angles with the positive direction of the x-axis. There it is. Okay, you see that? Yeah, you can see it, right? Now, see how it's moving? Okay, so it's exactly the same height as this red line, and it's moved over to the right from the origin here to reflect the angle, the size that this angle in here is in radians from the positive direction of the x-axis, right? That's what we're doing, okay? And there we are. Now we've just about reached the summit. That's the hump there, basically. Right, at that value, sine theta equals 1, which is pi on 2. Okay, pi on 2 radians. Now we're going to go over the other side. Now, this is getting closer and closer and closer towards pi radians, and you'll see that the size of sine is decreasing as the red line decreases in height. Yes? RCB. Now that don't pay any attention to that. That's supposed to be sitting over here, over there at that point there. The software just has a little glitch that I can't fix. Okay, that's all right. You get the deal, don't you? All right. So let's just do it the other way now with negative angles and see what we can do with it. Now, okay. Now I'm going negative clockwise. Negative. Okay. So this part here. This is the negative angular direction here, and you'll see the little sine gremlin start to trace to the left and go downwards as the red line in the triangle that I'm making is going more and more in the negative. Okay, you see that? Yeah, got it. Now we're at the, oh wait a minute, I'll go back. That's the summit where sine is -1, right? Negative pi on 2 radians. Sine is -1. Now we're going to make it go back towards ground zero as the red line gets less and less in the negative, and we go towards -pi radians. There it is. Okay, and you can see we've done it, guys. Now you can see how you trace out the graph of sine, and sine is an odd function because sine of negative theta, whatever theta might be, is negative of the sine of positive theta. You see? This brown graph over here is like an upside down version of this graph over here. That's what I'm saying. That's why sine is an odd function. Properties of sine, here it comes. Now that's the graph I've shown you there from 0 to 2 pi, whereas on the previous screen I showed it from -pi to pi. This is the traditional way of looking at sine, from 0 to 2 pi. Blue line there, the blue line I've just showed you is the period. That is the part of the graph which you can generate before it starts repeating the same pattern all over again. Okay, and the period is 2 pi. That's of sine. Okay, the amplitude, that green light I've just showed you there, is the distance, the maximum distance it can get to without any plus or minus, just the distance that it can get away from the central axis around which it gyrates. And its amplitude, that's what it's called, its amplitude is 1. Okay, the range, these red lines that you can see here, the range is basically the y values that the function can have, which goes from -1 to +1. When x is 0, sine of x equals 0. When x is pi on 2, sine of x equals 1. And I'm showing you the quadrants here. There's quadrant 1, there's quadrant 2, there's quadrant 3, there's quadrant 4. And as we know, guys, sine is positive in quadrant 1 and 2, and it's negative in quadrant 3 and 4, as the cast diagram has shown us. Actually, the cast diagram comes from all this stuff anyway, so it all makes sense, doesn't it? Right, now, if y equals sine of nx, then the period is 2 pi over n, and sine is an odd function because sine of minus theta is equal to minus sine theta. Alright, that was a big lot of information, but that summarises it, I hope, very well for you. Now we're going to do the same thing and generate a cos graph now. Now, I don't need to give you all the introductory palaver, so let's go. First of all, we'll launch into the positive angles and show you how the graph of sine is cos is generated. Of course, when you have a zero angle, cos of 0 is 1 because the horizontal line here, our triangle has collapsed into a horizontal line. The red line's collapsed to nothing, the blue line has become 1, so cos of 0 degrees is 1. And now we're going to progress around here, and you see how cos is getting less and less, still positive, because the blue line in this triangle is getting less and less, heading towards 0 at 90 degrees. There it is, 0. Now let's go over here now, and you'll see that cos is negative because we have a negative x coordinate here, and it's going to get more and more in size, so increasingly negative, down towards a full pi radians at the flat line position. There it is. Okay, now let's do it the other way. We'll go in the negative angle direction now. Okay, round clockwise around this way, and what do you expect to see? Yes, we're going to be tracing this away horizontally, and we're going to be tracing the length of this blue line here as our value of y. Okay, here it goes. Yes, blue line getting less, cos getting less, but still positive, heading towards minus 90 or minus pi on 2, where cos is 0. And here we go around the other side. Now, this is pretty interesting because now cos is negative again because we've got a negative x coordinate, and it's going to be getting increasing in size, so it'll be becoming increasingly negative. Getting right round there to negative pi. Oh my, don't worry about that. That's supposed to be negative over there. That's my little software glitch again. Alright, do you get it? It's pretty graphic. I hope it helps you really understand it. There's the graph of cos shown from 0 to 2 pi now, not from minus pi to pi as I showed you in the previous screen. Now, okay, what can we say about this graph? Actually, cos is actually the same as sine, except that it's out of phase by 90 degrees or pi on 2. There's the blue line represents the period, and the period is 2 pi. The green line there represents the amplitude is 1, same thing as sine. The red lines there represent the range goes from -1 up to 1 inclusive, and when x is 0, cos of x is 1, and when x is pi on 2, cos of x equals 0. Yes, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Quadrant 1 and 4, cos is positive, and quadrant 2 and 3, cos is negative, as you already know from your cast diagram. If y equals cos of nx, then the period is 2 pi over n, and cos is an even function because cos of minus theta equals the same as cos theta. Yeah? Right, now we're going to do some transformations throughout the nation. We're going to do dilations and translations, and then we're going to do some reflections. Now this is sine. There's the graph of sine from 0 to 2 pi. Okay? Now that's it. Sine x. Now this one here is sine of 2x. Okay? Because that is a dilation of a factor of a half from the y-axis. Yes? That's the way we say it. It's an x compression, actually. It's an X compression. Everything's squashed into half its normal size, but therefore we say it's a dilation of a factor of half away from the y-axis. That's how we say it, right? Now, this one here is the graph of y equals 2 sine x, so that's a y stretch away from the x-axis of a factor of 2. You understand that, don't you? Now we'll do a translation. This one here is sine x plus 2. Plus 2, we've moved the whole thing up 2 units, all right? Great. Now, this is, we're going to do some reflections now. Now, these get a bit confusing, so have a look at this. This is the graph of y equals sine x shown to you from minus 2 pi up to plus 2 pi. Let's go for it now. That's that one. Now that's the now this one here is the graph of, what is it? It's y equals minus sine x. So that means you've got a y reflection or a reflection about the x-axis. So everything's been tipped upside down. That point there, for example, goes down to this point here, and say this point here goes to that point there. Yes, so the x-axis is acting as the mirror. Yes. Now, have a look at this one, back to the y equals sine x graph again. This one here is, now look, this is so interesting, this is y equals sine of minus x. Now in this case, ladies and gentlemen, in this case we've reflected it about, well, it's an x reflection, so it's reflected about this y-axis. So in other words, let me explain. This, say this black hump here, that is reflected about this axis to go to this yellow hump here. Yeah? Or alternatively, this black trough here would reflect about the y-axis to get you this yellow trough here. That actually looks the same as the previous reflection. If you were astute enough, you would have noticed that. They look the same. I'll go back and show you. See, that was the reflected about the x-axis. It's a y reflection, and yeah, and then here we go. This one's reflected about the y-axis, which is an x reflection. They look exactly the same, but they're constructed in different ways, if you understand what I mean. Okay, there we go. Yeah, there it is without the black graph. That is the graph of y equals sine of minus x. Yeah. All right, you get that? Hope so. Now we're going to do the same thing with cosine, dilations and translations. All right, there's the basic cosine graph there. Now, here comes cos of 2x. Same thing with sine. It's squashed into half its width, right? Yes, this one here is the graph of y equals 2 cos x. So that's basically a vertical dilation of a factor of 2 away from the x-axis. And now we'll do a translation. That's moved up 2. That's cos of x moved up 2, so that the central axis that it gyrates around is basically at y equals 2 instead of the x-axis is the normal position, which is y equals 0. Okay? Yes, very good. Now this one here is the reflection again for cos. These are the reflections for cos. Okay? There's your basic cos graph from minus 2 pi to 2 pi. Yes, this one here is the graph of minus cos x. So everything has been reflected about the x-axis to get a y reflection of the y. Okay, so this pink line here, which is cos x, that trough point there would become that green hump point there, etc., etc. Yes, very good. Now this is the graph of cos again, and this one here is the graph of cos of oh yes, that's the graph of cos of minus x, which is exactly the same as the graph of cos x, because cos is an even function. So if you reflect around about the y-axis, guys, you make exactly the same curve. You make exactly the same curve because it's an even function. You get that? Very good. Now, what do we got to do here? We've got to sketch the graph of y equals 5 sine 3 theta, where theta goes from theta goes from minus 4 pi on 3 up to and including 2 pi. My oh my. Now I'm going to do this in terms of a traditional way of looking at transformations. Then in subsequent examples we'll do them more into the groove of the way we just usually do sines and coses, okay? Because of their peculiar and characteristics unique to them, such as amplitude and period and all the rest of it. So Okay, so let's go with this. What have we got? Let y equals sine theta equal the original base model template function, if you like, and we'll say y dashed equals 5 sine 3 theta dashed, which can be our transformed function. From that, we're going to make equation 2 into that form, which means that they're now in equivalent form, and then we're just going to equate equivalent terms. So we can say that y dashed over 5 equals y, and 3 theta dashed equals theta, therefore y dashed equals 5y, because we're trying to get y dash and x dash, because we're trying to get what the transformation steps are to get to the transformed function. And theta dashed equals theta over 3. So basically we have the following to get from theta and y to theta dashed and... Wait a minute, what have I said there? To get from theta and y to theta dashed and y dashed. Oh, I just fixed up a little typo there. Sorry about that. Right, that reads correctly now. Okay? Now, what have we got? We have got the following. We've got a dilation of a factor of 5 away from the x-axis because y dashed is 5y. And also we've got a dilation of a factor of a third away from the y-axis because the theta is only a third of its normal size, compressed into a third of its normal size. Okay, so so the amplitude is 5, and the period, the amplitude is 5. You can know from this, yes, and the period is 2 pi over this number, 2 pi over 3. That tells us a lot. Okay, that's a very important way to consider when you're looking at these sine and cos graphs. The amplitude and the period, because it sort of grounds you and it lets you realise what you've got to do with it. Okay. Now, because these are oscillating functions, they're oscillating around about the central axis, and they have a certain amplitude and a certain period which we need to know about. Hence, this graph has 3 cycles to the right, because if you see, look, it's 2 pi on 3, so that's a third of 2 pi, so it's going to fit 3 cycles into this bit here, and it's going to have 2 cycles here to the left. 2 cycles to the left, yes? So that basically that shows us what it's going to do. So here comes the graph. You ready? Amplitude 5, period 2 pi over 3, 3 to the right of the y-axis, 2 to the left of the y-axis, and there it is. There it is, guys. Does it make sense to you? Let's just put a few little points in there to get ourselves sorted out. Do you see? Yeah, it looks right, doesn't it? Okay, very good. There's one, there's another one. That's the I'm marking the periods off for you. Okay, there's one there and there's another one. So you got it? So can you see? Yeah, okay. So this is the first period from there to there. That's the second period from there to the axis. Yes, and then we've got another period to there, and another period to there, and another period to there. All right? Jolly good show, okay? So let's move on. We've got another one here. We've got to sketch the graph of this here and this here. Okay? Have a look. Have a look. Let's just absorb it and see what we can do with it. Okay? Alright, so for the first one, basically we know that f of theta equals minus 3 cos 2 theta. That is, now I'm just giving you a bit of a summary here. That shows you it's got a reflection. That's a y reflection, or it's a reflection in the x-axis. That shows you that it's got an amplitude of 3, and that shows you that it's got a period of 2 pi over 2, which is the same as pi. Okay? So that tells you a lot. If you can just look at that information, you should be able to do that by now, because you should be well and truly used to all these transformations. So I'm just doing it that way now, instead of the traditional way that I did in the previous example, working it all out with the dashes and all the rest of it. Okay? This is reading it off directly. So we have 2 cycles of an upside down cos graph. This means it's upside down. Okay, we've got, because we have to go from 0 to 2 pi, this means we've got 2 cycles if the period is only pi, and we have an amplitude. We've got an amplitude of 3. Well, that's pretty easy for us to absorb. 2 cycles of an upside down cos graph with an amplitude of 3. Okay, let's do it. You ready? Okay, here it comes, right? So therefore we've got that. There's 2 cycles of an upside down cos graph. There's some x-axis values for you, just to put it in perspective, and we've got it. Okay, we've got it. let's do the next one, and we'll do this one now. What is this one telling us? Well, that's 5 sine of minus 3 theta. Okay, and that's going from 0 to 2 pi. Apple of my eye. My oh my. So what have we got there? We'll write it out. Now, let's just summarise what we've done, what we did to it to get these transformations. That has got an amplitude of 5. That has got a reflection in the y-axis. That is an x reflection, guys, or about the y-axis, and we know that it's got a period of 2 pi over 3. Okay, 2 pi over 3. So we can see instantly a third of 2 pi is its period, therefore we're going to fit 3 cycles in. I would think, wouldn't you? I think so. Okay, so we have a sine graph, amplitude 5. Yes, this is the 5 to keep us alive. Yes, or there, right? 3 cycles from 0 to 2 pi, where the left, now this is the interesting bit here, where the left of the y-axis has been reflected to the right. Okay, the left of the y-axis has been reflected to the right. Okay, so here it comes. There it is, right? Can you see that? Does it look right? There's an upside down sine graph. It's got an amplitude of 5. And there's one upside down cycle, there's another upside down cycle, there's another upside down cycle, or I really should be saying they're reflections about the y-axis, but it just so happens, as I showed you a few slides ago, that if you have this kind of thing, reflecting left to right has the same effect as reflecting up to down, okay, with sine, alright? Yes, so that looks right to me, I think so. So, you happy? Very good. Alright, well we better move on. We've got a lot to cover. Now, what do we got here? On separate axes, now these are getting a little bit more nasty now, because these have got translations in them, okay? This has got a horizontal translation of pi on 4 to the right. This has got a horizontal transformation of pi on 3 to the left. Okay, so we better gird our loins, guys, and go for it, okay? Let's write it out and summarise what we've got. Okay, so what would you say? What would you say? Come on, what do you think? Well, I think it's got an amplitude of 3, and I think it's got a period of 2 pi over 2, or just pi, and I think that it's got a horizontal translation of pi on 4 to the right, okay? So what does this mean? What does this mean? It means that we have 3 cycles, because we're going, now just remember, this goes from minus pi to 2 pi, okay? And it's got a period of pi. So that's going to fit in 3 cycles of a graph, and it's got an amplitude of 3. You see there, amplitude of 3. It's got a period of pi, and it's displaced horizontally forward or to the right by a quarter of a cycle. Now I've put that in that way to make it clear to us what is going on, you see, because it's got a period of pi, so therefore pi on 4 is a quarter of a cycle. Okay, I like to think of the sine and cos graphs in that way if I can. So a quarter of a cycle is going from the starting point to the first hump or trough, as the case may be. Okay, so you get that? Yeah. Okay, let's go for it. Do you understand? Right, so there are 2 cycles. There are going to be 2 cycles to the right of the y-axis. There's going to be 1 cycle to the left of the y-axis. Yes? Now, this is the graph. Now, that's the starting point. You see, the starting point, I call the starting point as the original starting point that's been shifted to the right by pi on 4, or a quarter of a cycle. Now, you see, we have moved this graph forward by a quarter of a cycle from bottom of the trough to the neutral central axis position, right? So it really starts from here, and it goes forward there, like that, for a cycle, and then forward there like that, and then this bit here matches up with kind of like, that bit's missing, because we can the rest of it's missing because we're only going forwards to 2 pi. Now, from this point here, it goes back, it goes backwards Okay, right, and then that's a full cycle. Then it goes there like that. There, that bit there basically matches with that bit of the jigsaw there to make that last bit, so that we do have 3 complete cycles. Now, so what I said, when I said we have 2 cycles to the right of the y-axis, they're not really 2 complete ones. We have 1 cycle to the left of the y-axis. So I'll show you why I said it that way. This goes here. This is here. This is a full cycle. Even though it doesn't look like traditional sine, it is a full cycle because it's a translated forward by pi on 4 version of sine, right? Now here's one cycle, here's another cycle here, one from there to there. It sort of looks like upside down cos if you think of it that way, think of it that way. Starting from there, it sort of looks like upside down cos, from there to there, and then from there to there, right? So that is 2 cycles. And we had 1 cycle to the left, yes? Alright, that's what I was trying to say, alright? Here it is, there's the first cycle, there's the second cycle, and there's the third cycle. That's what I really mean. Alright? Okay, good. Yeah, I know, it's brain busting, isn't it? But this is the nature of circular functions. So that's what we've got to do. Now, I think we've got to do B now. Here comes B for you and me. Alright, this one's a cos, isn't it? Let's write it out. Let's write it out and see if we can make out what we're doing. And it also goes from a different domain. It goes from minus pi to plus pi. Oh my. So there it goes. Now let's write out what we think is happening to this graph. Okay? Its amplitude is 3. Yes, do you agree? Its period is 2 pi over 3. 2 pi over 3. And it's basically got a horizontal translation of pi on 3 units to the left. Okay, you get that? Alright, so what we've got here, I like to do a little summary of what's going on so I can get it into my head how to do this. We have 3 cycles because we've got a span of 2 pi and the period of this thing is 2 pi over 3. So we're going to fit 3 cycles in. It's got an amplitude of 3, it's got a period of 2/3 of pi, and it's horizontally displaced to the left by pi on 3, you see up here, and pi on 3 is half a cycle. Now, it takes a while to get your head around how to do these, but let's just summarize what I worked out. From the translated starting point where x is basically minus pi on 3, now if you think about that, minus pi on 3, we've got to go backwards to minus pi, so that means we've got 2/3 of pi to go backwards. That means we're going to fit one full cycle into the left of that translated starting point. Right? Yes. Now going back towards the right now, from the starting point, from the translated starting point, which is that x is minus pi on 3, we're going to fit in half a cycle from x's minus pi on 3 till we get to the y-axis. Yes. Then we're going to fit in the other half of that cycle over to x's pi on 3, and then from pi on 3 onwards we've got 2/3 of pi to go before we hit the plus pi mark. Therefore we've got a full cycle. We'll fit one final cycle in there. I think I kind of get it from that, but I'll draw you the graph and show you. You can work all this out yourself, and you'll need a bit of time to do it too, because it takes a while for it all to sort of trickle down into your head and sort of work out what's what. But I always like to start from the starting point. That's the starting point there. X is minus pi on 3, alright? Now, that's the graph. That's the first cycle, which gets half of a cycle to the y-axis and another half a cycle to the point where x is pi on 3. That's the second cycle. That's a full cycle up to the point where x is pi. And the third cycle goes backwards from minus pi on 3 back to minus pi. My oh my. And it does have an amplitude of 3. That point there is y equals 3. And it starts there. Everything's good. Now, how are you going? You okay? Alright, very good. Let's go on and we'll just finish this off with a bang. Now, on separate axes there we have to sketch the graphs of, these are yucky, yuck. These have got vertical translations. These have got vertical translations in them. So, fortunately for you and me, in this video we don't have to work out the x-intercepts, guys. We're just trying to get the shapes of the graphs, okay? So this one's 3 sine 2 times t minus pi on 4 plus 2. Yes, they've thrown the book at us. T going from, what's that? From pi on 4 to 5 pi on 4. Okay. Well, I get it. Well, they've been a little bit kind because that's a span of pi. That's a span of pi. This thing's got a period of pi. So it looks like we're doing one cycle, one period of this thing. Okay. Oh, and if we start from pi on 4, which is the normal starting point because it's been translated forward to a starting point to the right where x equals pi on 4, that means we're going to be starting where the x domain starts will be that's the normal starting point of the graph. So that's probably not so disastrous after all, really. Let's do it. Let's have a look. What do we got? So what have we got? Let's summarise. We've got an amplitude of 3. Yes, haven't we? Yes, we've got a period of pi. Yes, we've got a horizontal translation of pi on 4 to the right, and we've got a vertical translation of 2 units up. All right, now, you ready? So this is basically a one cycle, and its starting point is pi on 4, where x is pi on 4, and because it's been moved up by 2, y will be 2, and that's where it's going to start. Then it'll finish at 5 pi on 4 and 2. That's what it'll do. Okay, here it comes. There she be, Jim. Look, pi on 4 and 2, and goes through one full cycle. Because it's got a period of pi, that'll be 3/4 of pi, and that'll be 5/4 of pi. Pi everywhere here. Alright, but you okay? You're not all pie in the sky, are you? No, alright. Well, look, we're nearly finished now. Oh, thank goodness. Right, so what's this one? Right, yuck. Vertical translation again. Vertical translation, so let's just summarise it. What's the period of this silly thing? The period of this thing is 2 pi over 3. Oh, look! That's got a span of 2 pi over 3. Thank goodness. It's another one cycle wonder. So let's just summarise. What do we got? Amplitude of 3, a period of 2 pi over 3, and horizontal translation of pi on 3 units to the left, and a vertical translation of 1 unit down. Alright, okay, we can cope. So this is a one cycle graph of cos, and the starting point is going to be minus pi on 3, and because it's been moved... Now, wait a minute. Because cos would normally start at its highest point, which would be where y is 2. This has been moved down 1, so it's going to start at y is 1. Yes, and it'll move down to y at its lowest point. It'll move down to y is... Now, let me see. Y is 1. It'll be moved down to y is minus... wait a minute, I'm having trouble thinking here. Let's just have a look at it. Oh, there she be. Look at that. So it'll move down to, yes. What's that? That's 1. It's minus 3, isn't it? Yeah, that's right. So it'll move down from 1 to minus 1. That's its central axis there. And then from there down to minus 3 at its lowest point. Gracious me. So that's minus pi on 3 and 1 at its starting point, a full cycle over to pi on 3 and 1, and I think we're done. We're done. Alright, a lot in that session as I told you, but you are a star and you'll go far if you practice, and I'm getting out of here. All power to you. Go and do some practice and get really terrific at them, and we'll see you in the next exciting video. Okay? Bye-bye.